All right, in this video today, we are talking about right triangle trigonometry. So if you're not familiar with it, so let's kind of go through it, do some problems um, to kind of talk about what it is all about. All right, so right triangle trig, the definitions of trig functions. So hopefully you're familiar with them. If not, here are the 6 trig functions we are going to be dealing with today, and they all come from right triangles. So trigonometry is for right triangles. So with that, there is a right triangle right there on our left-hand side. The side that is opposite of the angle is kind of labeled with like these lowercase letters that are corresponding to it. So the angle A, opposite of it is the side A. Angle B, the opposite is the side B. And then this 90-degree angle C, the opposite side is this hypotenuse. So the longest side is the hypotenuse. And then it has 2 legs, the hypotenuse and the 2 legs. So angle A, the length of the side opposite of that angle A, and then because we're taking a look at it in that diagram, everything is being looked at from the perspective of this angle theta over here. So we can say that the length of the side opposite of theta would be A, the length of the side adjacent to this angle theta would be B. And that's kind of like how we're going to take a look at the trig definitions over here. So sine is the length opposite of the angle theta over the hypotenuse. So then I can say sine is going to be A over C. Right? So cosine, again, from looking from the same perspective of this angle theta, cosine is always the length of the side adjacent to the angle, which is B, over the hypotenuse, which is C. And then tangent is the length of the side opposite of the angle theta. So in this case, opposite of theta is A over adjacent, which is B. And again, these are based off where theta is, and they can always kind of change. So like, for example, if this angle, let's just call it like angle, this Greek symbol, I think beta, it would be completely different, right? The opposite for sine of beta would like be B over C, and so on and so on and so on, to get the idea. All right. So the other 3 properties. So the basic ones are the sine, cosine, and tangent. But then there are these reciprocal properties of sine, cosine, and tangent. So the reciprocal property of sine is cosecant, which is just saying you just flip them. So this becomes C over A. Secant is the reciprocal property of cosine, which is going to be C over B. And then reciprocal of tangent is cotangent, which becomes B over A. So those are the trig ratios, the right triangle definitions of the trig functions. So those are the six trig functions. 3 of them are the most basic ones that are used: sine, cosine, tangent. And then if like this is too much to remember, there is a saying that you can try to use this SOHCAHTOA, which is just smaller to remember it. So is just the sine opposite over hypotenuse. Ka is this cosine, which is the adjacent over hypotenuse, and then toa is the tangent opposite over adjacent. So with that, let's go ahead and take a look at some problems here. So in the next several problems, we're going to be finding each of the 6 trig functions of the theta. So step 1, which again looks like, let me erase some of the stuff that I clearly forgot to erase when I was preparing this. Okay, so here we go. So step 1, in order to find the trig ratios, is going to be, we need to know all the sides. So do I have all the sides? Clearly not. I have one of the sides missing. In this case, the hypotenuse is missing over here. So step 1 is we need to find C. So find C using Pythagorean theorem. Pythagorean theorem, right? So that is just going to be a squared plus b squared is equal to c squared. So in this case, 5 squared plus 12 squared is equal to c squared. So that's going to be 25 plus 144 is equal to c squared. Then remember, square root it up. So that's going to be C is equal to square root of 169, which is 13. So C is 13, and then we can use our knowledge of trig to fill in our ratio. So sine of theta is going to be opposite over the hypotenuse. So I'm just going to go ahead and fill this in side by side because it's a reciprocal property. Cosine is going to be adjacent over hypotenuse. So let's flip those. Tangent is going to be opposite over adjacent. And let's flip the cotangent. And there it is. That's how we find the trig ratios of a right triangle. Let's take a look at another example over here. So we have this right triangle, and then we have been given the hypotenuse, one of the legs, and we got to find the missing leg first. So step one is use this Pythagorean theorem to find it. So this is going to be 3 squared is equal to 1 squared equals b squared. 9 minus 1 is equal to b squared. 8 is equal to b squared. Take the square root. Then we can say b is, you always want to simplify square roots when you can. So this is actually going to be 2 root 2. You always want to simplify. Always, always, always. All right, so let's go ahead and fill these in. So sine is going to be opposite hypotenuse, so 3 over 1. Cosine is going to be 2 root 2 over 3. So this is going to be 3 over 2 root 2. Tangent is 1 over 2 root 2. So this is just 2 root 2 over 1. And one of the things, like if you've been told like, oh, you can never have square roots in your denominator, you got to rationalize. Well, the nice thing about trig is we can actually kind of ignore that. It's actually better to not rationalize your denominators when it comes to finding these trig ratios, even though, like, if you're familiar with the unit circle clearly rationalizes the denominators, but I would highly recommend just don't do it. You can definitely survive without rationalizing the denominator, and it's actually much better to make your life easy. All right, let's take a look at another example over here. So next we have, the only thing that's been given to me is like, okay, tangent theta is 7 over 4. Well, I know tangent, so like if I know anything about tangent, so tangent of theta is always, tangent of theta is what? Opposite over adjacent. So clearly this is the opposite side, this is the adjacent side. And then if it also helps, like one of the things I like to do is kind of like make a visual diagram of it. That is always beneficial. Right? So then let's label these sides in. So, you can put theta wherever you want. So let's just say if you want to put theta over here this time, right? Because the other examples we use theta like in the same place again and again. Let's just flip it up. So tangent is going to be opposite over adjacent. And then I have to find out what this missing side is. So I can say that C is equal to square root of 24 squared plus 7 squared. So C is equal to, this is going to be what, 49, and 5, so 625. So C is 25. And then we can fill in our ratios. So this is going to be opposite over the hypotenuse, which is 25. So this is going to be 25 over 7. Cosine is adjacent over hypotenuse. So whoops, not 25, 24 over 25. 24 over 25. So that means this is going to be 25 over 24. Tangent, we already know what that is. So that's 7 over 24. So cotangent is just 24, 7. And there it is. That's how we can find this information. All right, so the next thing is special right triangles. And at this point, like if you're not familiar, like, you're taking a look at this diagram, it's got some stuff filled in for what the expressions for the sides are. Like the short side, the side across from 30 is always labeled x. Adjacent is x root 3, and then the hypotenuse is 2x. So if you're not familiar, like, where these are derived from, I would highly, highly recommend watching the video that I have for the proof of the 30, 60, 90 and the 45, 45, 90. It's really, really crucial to understand where the properties of these come from, because then it just makes our life that much more easier to even understand the unit circle. So when we get into the whole unit circle part of it, it just makes our life easy. So again, I would highly encourage you to kind of watch the video of the special right triangle proofs. All right. So, but with that, here are the properties of special right triangles, and with that, our goal is to find the trig ratios. So let's do that. So here we go. Sine of 30 is going to be opposite over hypotenuse. So if I simplify it, I actually end up getting 1 over 2. I end up getting 1 over 2. And then if I do cosine, cosine is going to be adjacent over the hypotenuse. So if I simplify this, that is root 3 over 2. And then tangent is going to be opposite over adjacent. That is just going to be 1 over root 3. All right, so then cosecant, these are just the reciprocal properties. So this is just 2 over 1. This is just 2 over root 3. This is root 3 over 1. All right, so let's take a look at 60. So what do we got for 60? 60 is going to be x root 3 over 2x, so root 3 over 2. Cosine, what do we got for cosine of 60 is adjacent over hypotenuse, so 1/2. And then tangent, x root 3 over x, so that is just root 3 over 1. And then let's flip them to get the other remaining 1 over root 3. All right, so let's do the last one. It is going to be, let's see here. So 45. So now we're jumping into this right isosceles triangle. So sine of 45 is going to be opposite over hypotenuse. So that's 1 over root 2. Or, if I were to rationalize this, if wait a second, this does not look like a 45-degree one. If you're familiar with unit circle, you can say or root 2 over 2. It's the same thing. It's the same thing. And cosine actually ends up being the same thing, x over root 2. So either 1 over root 2 or root 2 over 2, exactly the same thing. That's root 2 over 2 just means we rationalize the denominator. So again, as I said, you do not have to. All right, tangent is just x over x, which is just 1. And let's flip them. So this is root 2 over 1, root 2 over 1, and then that's just 1. So those are the trig ratios of the 30, the 60, and the 45. And these are going to be super duper handy. So I highly recommend kind of like knowing them. And it's a really good idea to kind of like memorize these. These always come up non-stop when we are dealing with a lot of things we're going to do with trig. All right. So the last thing dealing with right triangles is going to be talking about, like, you might see some applications that deal with this, which is kind of like this angle of elevation and angle of depression. And it really just talks about, like, angle of elevation is like, let's say you're looking, straight ahead. There's a line of sight looking completely straight ahead. And then all of a sudden your eyes start to shift up. So your head is tilting up, looking at an object up above. That is what the angle of elevation is. And then if your head tends to shift down, we can make a right triangle using the angle of depression. So it's all about like the line of sight. Pretend like, you're looking completely straight ahead right now and start to look at the ceiling. And that little angle of your head moving up is the angle of elevation. Now, start to take a look at something on the floor, so that your head tilting down from looking straight to looking down is the angle of depression. So with that, let's just take a look at one quick little problem, and that will kind of be it. So what do we got over here? So we have the blue shading in the picture over here represents a lake. The distance A is unknown. So it looks like we're finding out what the distance is going to be for the lake. To find the distance, a surveyor took the measurements shown in the diagram. What is the distance across the lake? Round your answer to the nearest 10th. So let's see here. So that is going to be, I've been given the angle I've been given a distance from point A to point C. So let's see. So that is going to be from the angle opposite. So that's going to be tangent of 24 is equal to A over 750, opposite over adjacent. And then I can just use some algebraic manipulation. So A is equal to tangent of 24 times 750. And then using my calculator, I'm going to end up getting 333.9 yards. 333.9 yards. So the distance from B to C is 333.9. And that's it for right triangle trig.